It's the angular velocity. Angular velocity. Stop at 30. Stop at 30. Okay, very good. Yeah, so A is the right answer. Let's see, y'all are thinking linear velocity, and that would be correct if that's what y'all are thinking. I think that's what most of you are thinking. That would put C. C would be correct if it was linear, but it's angular velocity. Because...
Wait, A. It was answered. A. You put C.
Oh yeah, A. Which two of you got? Good job. Who was it today? Did you? Good. Twice? Or somebody else put it too? You didn't have to answer. It was a rhetorical question. But why do I ask rhetorical questions?
Because you want people.
You get it? Like that was a rhetorical question too. All right. All right. So Bonnie, same situation. Who has the larger tangential velocity or linear velocity? That's not omega, but v.
So, if the merry-go-round instantaneously disappeared out of existence, who would fly farther?
Right. All right. I'll stop at 40. Stop at 40. Why am I going to stop?
No. Someone else.
Okay, very good. B. Bonnie covers a larger distance in the same amount of time. So she, you have a question?
Finish with
She covers a larger distance in the same amount of time as Clyde because she's on the outer rim, and so she has a larger linear velocity. Yeah.
Going back to what you just said, that if the cliffs just disappeared for a second,
Mm-hmm.
would they, even though they would go at different velocities out, would they go to the same exact position?
No.
They will go to different angles.
Like we look at it from overhead, you know, this is Clyde and this is Bonnie, and at a particular point, you know, Clyde has a velocity looks like that, and Bonnie has a bigger velocity. These are the velocity vectors. So
What I'm pretty much asking, would they go still in the same exact direction?
they'd go in the same exact direction, but Bonnie would go a further distance than Clyde.
Okay.
It would become a projectile motion problem, right, where both of them would, if I look at it from the side here, they would both sort of follow a trajectory down to the ground. But since Bonnie has a higher initial velocity, she would go further. Okay. And that's a good point, because if you take away the merry-go-round, that removes the centripetal force. And what provides the centripetal force in this case? What provides the centripetal force? The what? Right, the carousel, but the static friction, somebody said it. Sure, the static friction between the merry-go-round and the bunny's little feet. Right? Did I mark that correct? Yeah. All right, suppose that the speedometer of a truck is set to read the linear speed of the truck, but it uses a device that measures the angular speed of the tires, which is what a speedometer does. It measures omega, and then it converts that back to V, which is what you read on your speedometer. What if you put larger diameter tires on the truck? How will that affect the speedometer reading? Stop at 50 seconds. Y'all answered this really quickly, usually. And you got it right, too. That's good. He's the right answer. Usually people get this wrong. Do y'all all ride bikes? Like bicycles with speedometers on them? You do? No, okay. Because on a bicycle, you have to put in the radius of the wheel, and you have to think about the size of your wheel. But so, let me just show you. I think y'all understand. Let me show you. So, normally my tire is this big. It measures the omega.
Drawing in a place that we can't see.
And V is equal to omega times R. But then if you put in a bigger tire, like you get a big old mud tire on your truck, that are a lot bigger than they were installed with, now it has the same omega, but R is bigger. And so since V equals omega times R, if R is bigger, then your car is actually going to be faster, going faster, but your speedometer still thinks that you have these little bitty tires on it, and so it's going to read a slower speed. Is that clear? Yeah, y'all seem to understand, so that's good.
Oh, I messed up the question. I was thinking the opposite.
All right. An object begins to rotate with a constant angular acceleration. This object rotates at an angle theta in time t. What angle does it rotate in time 1/2 t? All right, I'll stop at 55. 55. Oh boy, we're all over the place. So let me just remind you of our relationship between theta and t. It's omega naught t plus 1/2 alpha t squared. And here we're saying that it begins at rest, so that means that omega naught equals 0, so this whole term goes away. So we just have theta and 1/2 alpha t squared. Let's try it again. What happens to theta if I decrease t by 1/2? What happens to theta in that quadratic relationship? So if I make 1/2 t over here. Stop at 40. Stop at 40. Very good. B is the right answer. It's useful to be able to understand those relationships, how if I change one variable, how it affects another. And it often comes up, as I said before, on standardized tests. Speaking of standardized tests, I think I just have one person in here that's pre-med. Is that right? Just you, Andrew? Is there any other pre-med MCAT folks? Or maybe, okay, well, we're offering that MCAT prep course. I don't know, did you get my email? No? Okay, well, let me know if you're interested in taking it soon. It's going to be next semester, 1 to 4 on Friday. And you're in Organic 1 right now, right? You're in Organic 2, okay, so you qualify. All right, so if you're pre-med taking the MCAT, we're offering this MCAT prep course. So it just covers Gen Chem, Organic Chem, and Physics. It should be a good course. No? I know, I understand that now. Okay. Good. Yeah, y'all tell your friends there's still 4 or 5 spots. I think that the email might have just gone out to biology majors, so I'll touch base with all the chem majors too. All right, an object at rest begins to rotate with a constant angular acceleration as omega at time t. What is omega at time 1/2 t? Or what is the angular velocity at 1/2 t? I'll stop at 50 seconds. Very good. A is the right answer. Between omega and t, there is a linear relationship. If omega naught equals 0, omega equals alpha t. So if I take 1/2 t, I get 1/2 my velocity. This fan blade is slowing down. What are the signs of omega and alpha? I don't know if we said this explicitly, but you might remember from chapter 2 that if your velocity and acceleration are in the same direction, it speeds up, and if your velocity and acceleration are in opposite directions, it slows down. Did I say that explicitly? This chapter, I don't remember saying that. Do you recall? If velocity and acceleration are in these directions, it slows down. If they're in the same direction, they speed up. The same is true for angular quantities. I'll stop at 110. 22 people in here? Since omega is positive, what's the direction that it's going? Is it clockwise or counterclockwise?
Clockwise.
Right, and remember, clockwise is what direction in our rotational frame? It's negative. Remember, the clock goes around in the negative direction, so your clock is actually measuring negative time. Right, y'all remember like that whole thing? Let's just help you remember that. Clockwise is negative, and so if omega is negative, I have negative omega, and it's slowing down, that means I have what alpha? Positive alpha. Yeah, so omega is negative and alpha is positive. So B is the right answer. But it's good that both answers were opposite, so that's good news. So C is the next best wrong answer. Because they're opposite.
It's the least wrong answer.
Right. Are your wheel rotating at 5 revolutions per second has what approximate angular velocity? So just converting revolutions per second to radians per second. You can just approximate pi. Be 3-ish. Y'all ever watch Jimmy Kimmel?
Actually, I have.
I don't, because it's too late, but I've seen some of his stuff on the internet.
I saw one really cool where he made bowling balls flush.
Really?
Yeah.
He had a Skype interview with this lady. She was a high school student, but she took her calculator to the prom. Like, she dressed her calculator up in a little tuxedo and stuff. And took it to the prom. Alright, just a few more seconds. I'll stop at 1:15.
Can we watch that?
Yeah, I saw where.
No, we're not gonna watch that. You can you can do it for homework.
Okay. Where it's specifically a 10-pound bowling ball, I think.
Yeah?
And it'll float. A 10-pound will float. A 10-pound will hover. A 10-pound will float. An 8-pound will float, and a 12-pound will sink.
In what?
Water. Because the weight distribution is higher than 1 in a 12, while it's equal to 1 approximately 10,
Look at
and it's
that.
less than 1 in an 8.
Alright, so we're just converting this. In 1 revolution, there are 2 pi radians. Alright, so pi is about 6, or pi is about 3, so 2 times 3 is 6, so this is about 30, so D is the right answer. you could have just a basic conversion problem in the multiple choice, but also you're likely to see it in some of the free response. Remember, you will never go wrong converting to radians, because that is the SI unit. You will sometimes go wrong if you don't convert it to radians. Sometimes. All right, consider a child who is swinging. As she reaches the lowest point in her swing, I want you to think about this. I have a swing. It's going back and forth. And at the lowest point, which of these statements is true? Think about the sum of the forces that are acting on the swing. Stop at 115. Okay. Let's draw the force vectors here. I have how many forces acting on this girl? There are two force vectors. What are they? Or what's one of them? The weight, and then what's the other? The tension. Right, so I have the tension and the weight. The tension is acting in this direction, and the weight is acting in this direction. What is her acceleration, and what's the direction of her acceleration in this case?
Whatever way she's going.
No, towards the center, right? So it's up towards the center. It's the centripetal acceleration, right? Because she's moving back and forth, back and forth, back and forth.
And so she has a centripetal acceleration, and it's that acceleration that causes her to move in this circular path. So my acceleration is in this direction, AC. Now, I can do Newton's second law. Sum of the forces equals m times a, and that's going to be my AC. The sum of the forces is Ft minus Fw, and that's equal to MAC. All right, where A is not 0. Let's try it again. Stop at 50. Okay, look, A is not right, because the tension is not equal to her weight. Because if I just solve this for tension, I get tension as Fw plus MAC. Right, so her tension is actually more than the weight, right? Because I have to add in the second term, that mass times the centripetal acceleration. That's our centripetal force. Or rather, that is the additional force in addition to the weight. So it's also true that the tension in the rope isn't equal to her mass times her acceleration, right? So neither A nor B is true. What about C? Is that true? No, it's D. Yeah, so D is the right answer. I know that D isn't right very often, but every once in a while D is the correct answer. All right? We'll work through a problem, I think. We'll see. find one. All right, a rigid object is rotating with a negative angular speed, omega less than 0. The angular velocity vector and the angular acceleration vector are antiparallel. What does that mean, antiparallel? They're opposite directions, right? The angular speed of the rigid object is what? What's the direction? Is it increasing or decreasing? So first you want to ask yourself, is the omega clockwise or counterclockwise? And then is it increasing or decreasing? Omega is negative. All right, I'll stop at 115. See, it is clockwise and it is decreasing. Very good. So B. I have a negative omega, so that tells me that it's clockwise. And since it's anti-parallel to alpha, that means that I have a positive alpha. So that means that it's decreasing. So clockwise and decreasing because omega and alpha are in opposite directions. All right. Let's do a couple more problems. We'll look at some of the old exams and work through some of the old problems. Would that be useful for you? Work through one or two more problems. We're going to see more of this in Chapter 8 because Chapter 8 is really just a continuation. I think we've worked all the problems in the book, right? I need to put some more in there. We might have trouble doing this actually, because most of the problems are wrapped up with Chapter 8 problems. Okay, let's try this one. This is a good problem. A wheel has a constant angular acceleration of 3 radians per second squared. During a certain 2-second interval, it turns to an angle of 614 revolutions. Assuming that the wheel started from rest, how long has it been in motion at the start of this 2-second interval? All right, so first just write down everything that you know. All right, so pick out all the variables that you know. And notice that you have one that's in revolutions. Go ahead and convert that to radians. So go ahead and do that part. Don't worry really about what the question's asking right now. Just sort of assess what you know. And then we'll talk about what we need to know.
What test is this on?
This is Fall 07. Exam 3. Fall 07, Exam 3. Go ahead and convert that theta into radians. Somebody had that in radians, that 614?
3,157.1.
3860. So that's equal to 3860 radians. All right. So first of all, we don't know what omega naught is. Like this, we have this wheel spinning, and it spins for a certain amount of time, speeding up from rest. And then at some point, we start the timer, and we let it go for 2 seconds, and then it turns through that many revolutions, 614 revolutions. All right, so what's going to be our first step in this? We want to figure out, by the way, what was that duration of time that it moved to get up to that point where you started your timer. What's going to be our steps in this? I'm just going to write down our equations over here, so we'll sort of have them on the side. Omega is omega naught plus alpha t, theta alpha t squared. What should we do first?
The first interval.
The what?
Solve it first.
The 2 seconds? Solve it for what?
From 0 to 2, you traveled 614 revolutions.
Uh-huh. What are we going to solve for, though?
You're going to solve for, to find what you know theta, that's 614, well, that's 383,860. And you know the time, and you know the acceleration, so you'll solve for omega.
Omega naught, right. So we'll find what is that speed at which you start your stopwatch, which is omega naught. That's the omega right at the beginning of that 2 seconds. So we're going to solve for omega naught. So I say, let's see, I'll just put in the numbers here, 3860. Radians equals omega naught times t, which is 2 seconds, or it's 2.0 seconds, plus 1/2 of 3 times 2 squared. Somebody could solve that. What is it?
322.
No, that can't be right.
I got 1927.
Yeah, 1930. That's, or no, we'll call it 1927. We'll keep more sig figs than we need for now. Yeah, you must have had a mistake somewhere, Sean.
Which is the same thing as our original radians divided by 2.
What?
It's the same thing as our evolutions divided by 2. Our radians divided by 2.
Well, not exactly.
Not exactly.
Yeah.
It's 230. That's if we round it up.
Yeah.
All right. So that is our velocity at the beginning of that 2 second interval. But I want to know the previous time interval. So how am I going to find that time interval?
Use the first time.
The first what?
The first equation.
Right.
Equals omega naught.
So this thing rotates around for a certain amount of time. It starts. So now this omega naught, this will now become our omega final for the previous duration of time, which we want to know. So we say omega equals omega naught plus alpha t. Omega now is going to be 1927 radians per second. What is omega naught equal to? It's 0. That's at the very beginning when this wheel first started turning. omega naught is 0, plus alpha, which is given, that's 3, and then t. All right, so if I solve that for t, what is it?
640.
Okay, yeah, we'll just call it 640 seconds. So it rotates through 640 seconds for a time of 640 seconds before that 2-second interval when it rotated through 3860 radians. All right. These problems it's really a matter of reading them and picking out the information that you know. But that's a good skill to have. It doesn't apply just here, but it applies in all of your fields. All right. There aren't many other these explicit type problems because I wrap them up into chapter 8 usually on the quizzes. So we'll see some more as we go along. How do y'all feel about these kinematics problems? Not great, but okay maybe? Maybe not okay. But we're going to see some more when we get into chapter 8. All right, let's go ahead and look at chapter 8. Chapter 8 is really just a continuation of chapter 7. Whereas in chapter 7 we did kinematics, in chapter 8 we'll continue on with kinematics, applying Newton's laws to rotational motion, or particularly Newton's second law to rotational motion. We'll also look at angular momentum, the moment of inertia, which is the same as inertia in a linear frame. Remember what inertia, that was a measure of what? Or what is a measure of inertia? Rhymes with oh, what is it? What is it?
Like inertia?
Yeah. Oh, I'm sorry, I thought you got my
I don't
note.
know.
It's math, right? It's math. It rhymes with. Huh? Pass? Yeah, it rhymes with pass. What was I saying? Anyway, so we'll also get into surface or not surface, volume intervals, where we solve the moment of inertia for some rigid bodies, which those are kind of fun. All right, I'm going to come away from this. There are some more kinematics problems in the homework, which will be good practice for you.
Yay!
Guys, I'm going to tentatively cancel class on November 22nd. I hope that's okay. Like, you can go see the registrar and ask for your $15 back or whatever. I'm not sure how much it is per class. How much do y'all pay tuition for one class, you know? You have no idea.
I did the math one year that if you had a full 18-hour schedule or something, that you can pay like $15 to $20
A class? Per class?
per class.
Yeah, so you can go see Kelly Rodriguez. I'm sure he'll pay you back.
I think that comes out of your pocket.
No, I'm not serious. Don't tell him I said that.
Can we do it anonymously?
No, you may not. Where's my bag?
Maybe anonymous.
It's $15 about now.
Right. Alright, we're going to look at the cross product. You'll certainly see a cross product on the next quiz. So, it's similar to the, well, it's not really similar to the dot product. If you've had Calc 3, or you might have even seen cross products in high school, you might have learned a different way to do this, which might even be a little bit easier, where you lay out the vectors in a matrix form. I might show it to you a little bit later, but I'm going to do it sort of the roundabout way using the right-hand rule, because we'll use the right-hand rule next semester. I just want to make sure that you know how to use it. Let me just show you how to do the cross product. On my notes. Okay, the cross product is also called the vector product. Remember with the dot product, y'all remember what the other name of the dot product was? It was the dot product or the what? No, it was the scalar product. All right, so in contrast to the dot product, the product of a cross product isn't a scalar quantity, it's a vector quantity. So that's why we call it the vector product. It is the product of two vectors. and the result of the cross product is orthogonal to both of the vectors. Orthogonal. Oh, come on, y'all know what orthogonal means? No, you might not. Orthogonal means perpendicular. So like in a coordinate system, every axis is orthogonal to the other two axes, right? So the y-axis is orthogonal, or the x-axis is orthogonal to the y and z-axis. Orthogonal, 90 degrees. That's what orthogonal is.
Because they had to figure out another big word to call perpendicular.
They had to figure out another word to call perpendicular, but it typically means that it's perpendicular to two axes. We'll see that in next semester.
Did you like do that over copyright or something?
What's that?
It's just like
A copyright thing?
plagiarism thing where they're like, oh, you can't use the word perpendicular. Somebody else did that.
No, I think there's actually a mathematical definition that's distinct from perpendicular, but I don't know what it is. I think it might mean that it's perpendicular to two axes. I'm not, don't quote me on that. The magnitude of the cross product is equal to the area of the parallelogram that's bordered by the two vectors. And I have a figure here that shows that. So if I have two vectors, A and B, my vector B, my vector A, the direction of the product A cross B is orthogonal to both of those. Now notice that there are two possible directions that are orthogonal for these two vectors A and B. If these are vectors A and B, I can have another vector that's orthogonal to them that's either coming up in this direction or that's coming down in this direction, right? And there's we're working in a right-handed coordinate system, so we use something called the right-hand rule to figure out what is that direction, right? So in this case, my vector A cross B is up, and the magnitude of that vector A cross B is given by the area of this parallelogram. All right. Okay. So the area of the parallelogram is the base times the height, and this is going to be BA sine theta. So in terms of the vectors, then, we can write the magnitude of the cross product. A cross B is going to be the magnitude of A times the magnitude of B times the sine of theta. All right, so this is sort of one of our first rules, that the magnitude of the cross product is AB sine theta. This is different from the dot product, which, remember, for the dot product, the magnitude of the dot product, or rather, the dot product was AB cosine theta. If we had A dot B, it was AB cosine theta. It had a slightly different physical meaning, but here our magnitude is AB sine theta for our two vectors. This comes up in a lot of different ways in physics. When you want to take the product of one vector with the component of another vector that's perpendicular to the first vector. That doesn't make much sense, does it? It'll come up in several different ways. It'll come up in rotational motion with torques, which we'll get into in Chapter 8. And then it'll also come up again next semester when we do magnetic fields. And then later, if you're an engineer, when you go into fluids, cross products come up quite a bit because you have a lot of rotation. And those types of forces are often, cross products become relevant. So you'll see those again in upper level courses. And you see them again in Calc 3 as well. I think it's Calc 3 here, vector calculus. All right, so let's consider two vectors. We'll just do an example. Let's say that I have a vector A that is AXI plus AYJ. And then I have a vector B that's BXI plus BYJ. And then the cross product is going to look like this. It's going to be AXI plus AYJ crossed with BXI plus BYJ. Now we use FOIL to expand out the product. And that product's going to look like this. AX, BX, I cross I. So just like we did with dot products, I'm just multiplying these two terms, the coefficients of the I vectors, and then I take the cross product of I cross I. We did this with dot products where we multiplied them out and we had like I dot j, all that jazz. We're doing the same thing here. We're just multiplying the coefficients and taking the cross product of the vectors. Outer is going to be AX, BY, I cross j. It's very important to get the order right because I cross j is not equal to j cross I. So if you switch them in the cross product, it's going to give you a different value. It's actually the negative. I cross j is equal to negative j cross I. We'll see that in just a bit. That's outer. Inner is AYBX times what? If I do my inner, AY here, what's my cross product? J cross I. Not I cross j, but j cross I. Plus the last, which is AYBY, j cross j. Now some of these are going to go away, just like we had with dot products. Remember, some of them became 0. Which terms do you think are going to become 0? The similar terms, like I cross I, or the dissimilar terms, like I cross j? Dissimilar? Well, it is similar. Why is that?
You're not using the I dot I will be the vector drawn after using the symbol of the.
Right, using the sign, right, and the sign of 0 degrees is 0. Remember, the magnitude of your cross product is AB sine theta. So if I was to take the magnitude of I cross I, it would be 1 times the sine of 0, and the sine of 0 is equal to 0. So I cross I and j cross j are both going to go to 0. I cross I equals 0, and j cross j is also equal to 0. Remember, I'll write this over here. I cross I equals 1. That's the magnitude of I. Times 1. That's the magnitude of the second I. Times the sine of the angle between them, which is 0 degrees. And that's equal to 0. All right? Now, so now we need to figure out what is I cross j and what is j cross I. And that's where our right-hand rule will come in. You can do your right-hand rule in a couple different ways. I'll show you 2 different ways. And again, there is a matrix method to do these cross products, and if you've done that before, then you're welcome to do it here. If you've done it a lot, you might find that a little simpler. So you can take your fingers like this. We use our right hand because we use a right-handed coordinate system. If we let our index finger be A, our middle finger be B, then our thumb gives the direction of our cross product. So if these are my vectors A and B, then my thumb gives my cross product. Another way of looking at it is you let your fingers go in the direction of the first vector, and then they fold towards the second vector. I usually do it that way. Fingers in the direction of the first vector, and they fold towards the second vector with your right hand, and then your thumb gives the direction of the cross product with your right hand. Right hand. Your right hand. That's your left. Right.
It's all the same to me. Depends on what perspective you're looking at.
Oh, okay.
Whose left are we talking about? Mine or yours?
All right. So then you find the results of the vector cross products with the right-hand rule. Let the fingers, or excuse me, let the index finger of your right hand go in the direction of the first vector, and the ring finger or middle finger in the direction of the second vector. Or alternatively, you can let the fingers go in the direction of the first vector, and they fold towards the second vector. Don't worry, we'll get some practice with this. So if this doesn't make sense to you, you'll get practice, especially next semester. All right, and then the thumb of your right hand gives the direction of the cross product. Okay, so let's say I want to find I cross J.
If you do that, you're flipping somewhere else.
All right, I cross I and J cross J are 0 because they're in the same direction. Well, let's say I want to do I cross J. I'm going to draw my coordinate system here. This is my I axis, this is J, and this is K. Okay, that's my Z axis. K comes out of the page. So I let my fingers go in the direction of I, and then they fold towards J like that. Or I let my index finger go like that, and my middle finger points at J. I find it easier to do it this way. And then my thumb comes out of the page. So what is the product of I cross J? What is it equal to? What vector? K. It's equal to positive K, in fact. What is the product of J cross I? It's negative K. I'll show you. But this just brings up something that I cross J is equal to the negative of J cross I. And that's always true. Any two vectors, if you switch the position of the vectors in the cross product, the result is negative. So J cross I, so my fingers go in the direction of J, they fold towards I, and then my thumb goes into the page, so that's a negative K. All right, so then our cross product, and we'll wrap up here, is AX BY minus AY BX. That negative comes about because of this J cross I in the K direction. All right, we'll stop there. We'll see cross products. You'll certainly see a cross product on the next test, but we'll see cross products as it comes up when you're calculating torques, because torques are the products of two perpendicular vectors, a force and a moment arm.
What day are we on?
Oh, the 22nd, but I'll give y'all a heads up. Our little boy's going to the zoo, huh? We might actually have class, because he doesn't leave till 8:30. I don't know, we'll see. I expect one off day between now and the end of the
I
semester.
thought it was talking about today.